Now let me call upon Sachin to introduce our next speaker.
Thanks, Sanjay. The next speaker will be Mr. David Hick, Technical Sales Manager, Autodesk. So David is a graduate in mechanical engineering and began his career as a simulation consultant in motorsports industry before moving on to the technical sales role. In 2005, David joined as a Blue Ridge Numerics, where he helped CFD Design becoming the fastest growing CFD product in the world before acquisition by Autodesk in 2011. For the last 20 years, David has been helping manufacturing and construction companies in Europe, India, and Latin America to incorporate simulation tool in the design process, thus enabling the designers and engineers to better understand the impact of design decision at the earliest possible stage. David's experience has extended across many industries, including consumer products, automotive, medical, defense, industrial machinery, and building constructions. So with this, I hand over the podium to David for the presentation. Thank you.
Thank you very much. Thank you, Sachin. Thank you. And welcome everyone this afternoon to our session on CFD for fluid flow and thermal management. So a brief agenda for the next 30 minutes. I'm going to present to you on why our customers at Autodesk are performing simulation, what is Autodesk CFD, the product options for Autodesk CFD, and I'll talk you through some examples of where our customers are being successful using this technology in industry. And if I'm quick enough, there might be some time for some Q&A, some questions at the end of the session. So why do our customers perform simulation? It really comes down to three main reasons. Firstly, to validate their designs, to understand how they're going to perform before they're manufactured and used in the real world. They perform simulation to optimize their designs, because often designs are a compromise between different characteristics, for example, strength and weight. And thirdly, they perform simulation because it reduces the reliance on physical testing. So physical testing is very time-consuming, can be very expensive, it provides limited insights, and there's many products where they simply can't be tested physically at all. But really what it boils down to are business reasons. So the reasons why our customers are performing simulation is because products are becoming more complex, they require greater efficiency, greater reliability, greater quality, and of course that limits the amount of opportunity for physical testing to prove and improve a product. And so this is also offset against a backdrop of greater competitive pressure and increased legislation. So really what we're seeing is that simulation has been moved from something that was a nice to have to something that's becoming very much essential. So if we take a look at a typical product development process in manufacture, so from the left, going from concept all the way through to manufacture and having the product launched into the market on the right-hand side, what we know is that the ability to make design changes that improve how a product performs actually reduces over time. And that's because over time, more and more constraints are put on the product. We get to a point where we manufacture the product and place it into the market. It becomes very expensive to make a change. So the costs increase. Of course, if we have a product in the market and there's a problem, it becomes a product recall. So that's expensive and it affects the reputation of the company, of the brand. However, if we make changes at the concept stage, at the earliest opportunity, it comes at no cost. So this is the kind of best time to innovate and come up with new ideas. But really, we need to test them at that stage. So having spoken to many of our customers, what we know is that on average, our manufacturing customers are testing their new products approximately 7 times. So there's 7 iterations, 7 tests performed on a new product design per product launch. Now, if that product is still not functioning at the end of that testing cycle, then the product could be going to market too late. It could be going to market with potential problems. And of course, if not enough tests are performed, then there could be reliability and quality issues. So what we're encouraging our customers to do is to look at performing simulation, so testing their products virtually at the earliest opportunity. So this way they can test different designs, different solutions, look at the use of different materials, different technologies, and they can really try and prove out the design before it's manufactured and before it's tested. So really, this is all about risk mitigation, getting to that final test, that final design with greater confidence as an engineer. So the power of simulation is really making better decisions sooner in the design process. So with this in mind, Autodesk have developed quite an extensive portfolio of simulation solutions, really through acquisition. So as a company, we've spent close to $500 million on acquiring companies and simulation technology. So we actually have a portfolio of simulation solutions that really rivals ANSYS in terms of the breadth of applications which are covered. And then back in 2011, Autodesk acquired a company called Blue Ridge Numerics, and Blue Ridge Numerics since 1992 had developed a piece of software called CFD Design. And so CFD Design has now become Autodesk CFD. The reason why I mention this is because it's not new technology. It's been around for over 20 years. And for that period of time, as Sachin said, Blue Ridge became the fastest growing CFD company in the world. So it's a well-trusted, well-vetted solution. But from the outset, the product has really been developed for engineers. It's not a specialist tool. So what is CFD? There's a bit of a running joke with this, that CFD stands for Colors for Directors. So a nice way of coming up with a nice color plot that you can present to your manager to show how a product's performing. But actually it stands for Computational Fluid Dynamics. That's a study of different fluids that could be liquids or gases, but also the study of temperatures. So 80% of our customers are using this technology for trying to manage heat within their designs. So initially, the technology started off in the motorsport and aerospace industry. So it's being used by customers to look at external airflow around their designs. And then this rapidly moved to looking at the flows inside products. So the flows inside valves, pumps, ducts, engines, as we see here. And then we introduced the capability for our customers to study temperatures. And that opened up the world of electronics and consumer products. And of course, if it's possible to look at fluid flow around a vehicle, it's possible to look at fluid flow around and in between buildings. So the biggest growth area in the use of CFD at the moment is in the AEC space. So you might argue I'm actually in the wrong room, but that's actually where we're seeing a lot of interest in the use of this technology. And of course, if it's possible to look at fluids or fluid flow inside a product, it's also possible to look at fluid flow inside a building or a factory. So it's possible to simulate a factory space, the heat given off by equipment, by people in that space, and understand that the temperatures comply with legislation. So the uses for this technology are very broad. So as I mentioned earlier, many of our customers perform physical testing. And physical testing is very limited. So we can see here an image of a gentleman performing a test for a pump, a new pump design. And so the pump is on a test bench. There's water passing through the pump at a certain pressure. He's calculating what the flow rate is for the water passing through the pump. If the pump fails, if there's a problem in terms of the expected flow rate, what does he do? So the physical test just provides a kind of yes or no answer. It doesn't give him any more information to help him improve how that product's working. So maybe it's the impeller, maybe it's the shape of the volutes. There could be some other parameters that he could investigate, but he doesn't know what to try next. And of course, these could be very expensive to prototype. The cost could be very expensive, so that limits his options. So through the use of simulation, it's possible for a designer or engineer to really visualize what's actually happening inside a product. And when you can visualize what's happening, you can identify potential problems. Of course, you can also optimize the design as well. So a big part of this is visualization. So being able to kind of look inside a product and using your computer as a virtual test bench. So being able to visualize what's happening in terms of fluid flow, being able to visualize how the heat moves through an assembly. So put in simple terms, we've got an example of a valve here. We've got a lot of customers that produce these products. So it's important to be able to visualize how the fluid moves through the valve. Where is it moving faster? Where is it moving slower? Are there areas where there's recirculation in that fluid flow? Because that indicates some inefficiency. What happens if there's particles inside the fluid? Those particles could cause erosion. So there could be mechanical problems introduced. And then in terms of pressure, so the pressure is important to know because the pressure exerts forces. So what is the pressure distribution through the valve? What are the forces on particular surfaces? So where we have the valve part here, if we know what the forces are underneath the valve, we'll know what the stiffness of the spring should be that keeps the valve in place. So this is important data that's useful for the engineer. Of course, if we're dealing with a liquid, then we could potentially have this effect called cavitation. And that occurs at very, very low pressures, where effectively the water boils off. And that can cause mechanical problems with individual parts in the assembly. And then in terms of heat, if we have an assembly with different materials, then we've got varying rates of expansion and contraction. So in the case of the valve, it could be that we could have issues with leakage. So if we've got two parts expanding at a different rate, then we introduce openings where the fluid could escape. So these are all important characteristics that can affect the performance and quality of the product. So it's essential the engineer has a handle, an understanding of these quantities. Now, I've talked a bit about kind of fluid flow applications with pumps and valves, but many of our customers are also involved with thermal cooling, particularly of electronic systems. So there the challenges are understanding not just the temperatures and how the temperatures distribute through a design, through a product, through an assembly, but understanding why the temperatures are at that particular temperature. And often it's caused through airflow. So many of the products that we design are cooled by air. Maybe that air is transported by fans, maybe it's through natural convection. But then it asks the question, are the fans in the correct position? What kind of fans should I use? Can I avoid using fans because they're expensive, it adds weight, and it adds noise? So these are all challenges that designers of these products face. And of course, through physical testing, there's no guidance in terms of what they need to do to try and make a design perform better. So here's a quick example of the visualization. So this is a very simple hood that goes on the top of a chimney. And the idea here is to allow exhaust gas to escape from a chimney, at the same time preventing rainwater to enter into the chimney system. So it's a very simple product, but this goes through extensive physical testing on a test bench, and then the company would produce a specification. So this would show the flow rate of air excuse me, through the hood against a variable pressure loss. So again, if there's problems with the performance, they go back to the drawing board, they guess what they need to do, they discuss it as a team, and they experiment to try and find a solution. A better alternative is actually being able to simulate this. I'm going to jump on here for 1 second. There we go, that's better. So what we're seeing here is a representation of how the air is actually moving through the hood. So the colors of those flow traces indicates the speed. So understand how the air is going to move, if it's smooth or there's recirculation. This is showing an ISO surface, so that's showing areas at a certain speed or temperature, so I can see the flow balance through the hood. And now we can create a cross-section, as we would in the CAD system. The cross-section could show, for example, velocity, but also with arrows indicating the direction that the air is taking through the hood. We can change what it's showing to show pressure. Pressure will show us areas where there's higher pressure or lower pressure acting on that component, which is preventing the rainwater coming into the hood. But we can also calculate what the forces are. So that's important because as the air is pushing up against that component's going to be welded to the casing. Are my welds going to be strong enough? Or is that component going to fail and fall through the chimney? At the same time as we see here, we can investigate different design options. So one of the key advantages of Autodesk CFD is this ability to not just look at one design, one configuration, but to make multiple design changes and try and understand the merits of each of those individual design changes. So the product's configured in 3 different levels. So there's a basic level, which covers standard fluid flow and heat transfer. And that's taken and built upon with the advanced level, which allows our customers to look at effects that could be varying over time, the effects of radiation, and the effects of including what's called a fluid-free surface. So if, as you can see in the example here of the of the tanker is representing a vehicle that suddenly stopped moving, and that fluid has inertia. So as that fluid's moving, it's putting a force on the plates inside the tanker. It's going to calculate for us what those forces are, so we can make sure those plates are going to be strong enough. The third level of the software is a motion level, which is pretty cool. So this allows our customers to look at moving parts inside the fluid. So for fans, pumps, compressors, actuators, but it could be the fluid is moving the parts, such as a turbine. So it's possible to simulate any kind of fluid motion inside the analysis. So what are the reasons why more people are not using simulation, particularly CFD? And it really comes down to perception. There's a view that CFD is something which is difficult to use, or the results are quite limited, that it requires specialist hardware, and also that it's time-consuming and also expensive. And to a large degree, these perceptions are true with traditional CFD packages. So traditionally, they've been quite expensive. They can be quite complex and time-consuming to learn, and they're often driven by specialist users. So our approach over the last 20 years is to provide this technology in such a way that designers and engineers can readily access this and drive it and improve the performance of their products through getting accurate results quickly. So what we're doing is we're breaking down these traditional barriers. So the majority of our users are in fact engineers, designers, architects, product engineers, process engineers. They're non-specialists. So these are people that would use the software for a couple of days on a project, but they have many, many other tasks. They'll put it down, carry out their other tasks, come back to it next week and work on another project. So it's very much built for the multitasking engineer. And because it's engineers that are driving this, it's important that the product's integrated into the CAD system. So for that reason, our CFD tool integrates with all major CAD systems, not just Inventor and not just Revit. And it's fully associative, parametrically associative with all those systems. So if you make a design change, that propagates through into your simulation, just as your assemblies and your drawings would automatically update. Your simulation model automatically updates as well. So this is not to say that what we're offering is something that replaces traditional analysis tools. It's very much complementary. So many of our customers, particularly in large companies, have analysis departments. So there'll be folks where this is a full-time job. They'll be simulating quite high-end problems. But what we find when we've spoken to customers is that the designers, the engineers, often have designs that they're working on where they just want a quick answer. They just want to understand what the temperatures are inside their products. Or if they're developing the design for a valve, they just want to quickly understand what the flow rate is, or if there's any issues in the way that the valve has been developed. So what we found is that often the engineer is then having to export some geometry, which is then sent to the specialist who's using a different system, so it's not the same workflow, and the specialist would then prepare the geometry, the mesh, calculate the results, maybe send a report back to the engineer, which says yes or no, and then the engineer has to make a decision on what to do next. And of course, if the results are not good, this loop starts to repeat itself. And what we found in speaking to customers about this is this just causes frustration. So the engineer's frustrated because they want to get results now, today, and often the specialist is frustrated because they want to get on with something more challenging. So what we're trying to encourage is companies to adopt our CFD solution as very much an upfront tool, part of the design process. So the engineers and designers can run their own analysis, iterate their designs, develop them, get them to a point where they're happy, they're confident it's going to work in the real world, and then it can be passed to the specialist for verification. It's a much more efficient process, much more efficient workflow. Now, I mentioned there are other barriers as well in terms of hardware, time, and also cost. So in terms of hardware, no specialist hardware is required, but one advantage in our products is the ability to be able to solve on the cloud. So you've probably heard a lot about the cloud today for different applications. When it comes to simulation, that's where you really see the advantage of using the cloud. So our simulation products have been available for the cloud for, I think it's the last just over 4 years now, maybe almost 5 years. And so that gives our customers the advantage of not just solving a simulation sequentially, one after another, which is the traditional approach on a desktop, but being able to solve multiple analyses simultaneously at the same time. So if you have different concepts you want to test, or different environmental conditions, or different load conditions, they can all be calculated at the same time that it takes to run one on the desktop. This is really cool. But this year, we've seen a marked change because we've brought out something called Autodesk CFD 2. And this leverages a new cloud platform from Amazon Web Services. So the way this works is that when our customers are performing a simulation, the simulation goes to the cloud, but it accesses a cluster on the cloud. It's distributed computing on the cloud. A single analysis has access to over 256 cores, one analysis. So what that means is that the computation time becomes almost negligible. So where an analysis would have taken, say, 30 minutes in the cloud previously, we're seeing 3 minutes in the cloud at the moment. So it really means that you can test the product in many, many different ways and completely mitigate risk at the earliest opportunity. So some sample applications. And this is quite challenging because the product's being used in so many different industries. As you saw earlier, from automotive, aerospace, medical, of course also in the building, construction industry as well. So a couple of sample examples for you from our customers, and these have been presented at various events in the past. So the first one is from the oil and gas industry. It's actually a drilling head. So this product would be downhole drilling for oil or gas. And the challenge here is that if there's a failure of the cutting head, if it breaks or if there's erosion of the cutting head, then it's significant downtime to lift this thing a kilometer out from under the ground and repair it or replace it. So the time it's not spent drilling is costing the company a lot of money. Now, the way this product works is that there are nozzles which you can probably just make out. And these nozzles, through the nozzles, water is pumped to clear the debris away from the cutting head. And that keeps the cutting process working. Problem is, the water is not clean water. There's often debris, there's rock debris in the water. So what happens? The nozzles become eroded. They start to wear down. So this is a big challenge. So this customer, it's a big multinational company, were looking at a way to try and understand how their designs were performing. And these are complex shapes. There's nothing simple about this geometry. It's a few moving parts, but the actual profiles are very complex. And so this company had no previous experience of using CFD, but they did have access to an analysis department. And so what they found is that they tried to access the tools being used by the analysis department, but they struggled. It was taking around 2 weeks to actually come up with a workable solution. But the big advantage of using Autodesk CFD is it provides a perfect map to the CAD geometry because it's CAD integrated. So a model as complex as this can be represented rapidly in the CFD tool, and of course then it can be solved on the cloud very, very quickly. So the guys were impressed with the ease of use. There was a few mouse clicks to actually take a CAD model to a point where they could start running a simulation. But what really impressed them was the quality of the results. So the results were actually showing shear stresses on the surfaces of the cutting head, which mirrored where they were seeing product failure. And that gave them a huge amount of confidence that they were driving the software in the right way and getting meaningful results. The second example is very typical of the kind of products that our customers are using this software for. Pumps are one of my favorites. And this is a company that manufacture pumps for flood situations. So these are very large centrifugal water pumps made from cast iron. So as you can imagine, it's very expensive to prototype these kinds of products. And this was a company that, again, had no previous simulation experience. They had a young group of engineers, graduate engineers that had just joined the company, and they had some mechanical analysis experience. So the term simulation was not scary for them. They felt confident that they could pick up this software and have some success with it. And here we can see the test laboratory. That rather looks like my house at home. It's a bit of a mess. But you can see, you can probably just make out under all this mess, there are a couple of pumps. So this is the testing laboratory. And so what they would do here is vary the pressure head of the water, measure the flow rates, and then that would calculate a performance curve. So as I mentioned earlier, there's no way to see inside the pump as they're testing it. And so using CFD, it's possible to actually visualize, and the engineers could really understand what was happening as the impeller was rotating and driving all that kinetic energy in the fluid and turning it into static pressure for pumping. And so they could identify the effects of changing, for example, the profile of the impeller blades, the number of impeller blades, and the shape of the volute here, the expansion chamber. Because subtle changes here can have a huge effect on how these designs perform. And often what our customers here are looking for, they're not really looking for super accurate results. What they want to look at is comparative effects as they change the design. And if they can make a 1% improvement in efficiency, or flow efficiency, that's huge for them. That's a big win. And what these guys found that in the first project that they were working on, they're actually able to make an 11% improvement in efficiency. So either that shows they're using the software very well, or they had some very bad designs before. But a 1% improvement is certainly a good goal to aim for. Now, switching over slightly to thermal cooling. So the majority of issues with motors, and of course any devices where there's moving parts often involve motors, but where there's failures, in the majority of times, it's down to cooling issues. Too much heat inside the motor on the core. And this is a nice example from one of our automotive, in fact, motorsport. It's a Formula One manufacturer from the UK. And what they were developing was something called a KERS system, a kinetic energy recovery system. So basically, when a person is driving a car and they put the foot on the brake, that energy is stored into batteries or a flywheel so it can be used later on. So it's a nice example of sustainable technology, green technology. Now the problem with these products is that they can get very hot. And this is always the challenge with the use of energy recovery systems. So what we're seeing here is a cross-section through the motor generator. So what we have is a rotor, and this is the stator in a fiberglass enclosure. And this is a cross-section through the web where there's a copper windings wound around the web. And what they're finding is that this was melting. It was actually getting far, far too hot as it was charging and discharging. And they didn't know how to cool this. They didn't know where to begin, where the problem was being generated. But by looking at the results of a CFD analysis, they could identify that the temperatures were in fact uneven. So that's the first thing they noticed. They then noticed that the temperatures were exactly what they measured during the test, which was far too high. So that again gave them confidence that the software was accurately predicting the real world effects. And then they looked back in the design and decided, right, what we're going to do is we're going to add an additional cooling path here. So this is actually water cooled. I think mixing electricity and water, I'm not sure it's a good idea, but for these guys it seems to work. So there's water passing through the cooling channel here, and now here, much closer to where the stator is located. And so that had the net result of creating a more uniform temperature distribution and lowering the temperatures as well. So that was just one iteration of the design. Just in the interest of time, I'm just going to move forward slightly to a last example. So just mixing things up a bit here. So this example is actually an HVAC example from a company in the US that provide ventilation equipment for hospitals. And it's quite an interesting case study because last year in the US, around 1.7 million infections were contracted from hospitals. So basically, a patient had gone in for a routine procedure, and they'd actually contracted a secondary, more serious infection. And that actually led to over 100,000 patient deaths in the US. So it's a significant problem. And of course, that introduces some legal issues. So I think the healthcare service were, receiving suits adding up to around about $33 billion US. So this is a significant problem. They didn't know what was causing this. So Huntair, the company, what they did is they simulated a series of different operating theaters in hospitals across the US and how their existing ventilation systems were working. And what they found, and you can see this very clearly in the results, is that as the airflow was entering into the operating room, debris was being picked up off the floor and deposited onto the operating table where the patient was having the surgery. this was the root cause of the infection. So it's very much an HVAC challenge, an HVAC challenge. So Huntair developed a solution which provides a nice streamlined laminar flow of air from the air conditioning system in the ceiling down over the operating table and over the surgery staff as well. Now, they didn't stop there. So as well as developing a product, they also used the software to provide a service, because every room is going to be different. Every room has a different configuration. It's a different size, a different shape, and there'll be different equipment inside the room. So what they then were able to do is show how the product would function for a specific room size and shape. And they were using scan data to capture the inside of an as-built operating theater, representing that in the CAD model, and then showing the clients exactly how their product was going to perform. So it's a really good use of the technology, but expanding it as a service. So in summary, Autodesk CFD, it's very much designed for the non-specialist, so the casual user, the designer, engineer, or architect. It's integrated with all major 3D modeling systems. It's automated, so as a user, your focus is very much on looking at results and interpreting results. You're not spending time preparing geometry or simplifying models or creating meshes or copying analyses. All of those steps are automated for you to get you to look at results as fast as possible. It's flexible in terms of access. So again, we use a subscription model. So it's there for you as the projects dictate. If you've got a project this year, you might not have a project next year. So you have the access for 1 year. And of course, it supports cloud processing. So you have the ability to solve locally or in the cloud. And as we've seen here with some of the examples, there's connections with the visualization tools that we have from Autodesk as well. And this has been used a lot for helping our customers secure business at the bidding stage, so they can demonstrate to their clients that they have the technology to solve their problems. And above all else, it's fast. If it took longer than physical testing to solve, then it doesn't really have much value. But as I mentioned earlier, through solving locally or solving on the cloud, it's possible to actually run simulations, multiple simulations, in a matter of minutes to understand the effect of multiple different designs. So thank you very much for your time. I think I'm just on. But I should have enough time for some questions. Yeah, thank you. So any questions from the audience? Yes, sir.
One time I remember CFD would mean, do you have the right boundary conditions so that you get the right results? So does AutoCAD CFD also help in a menu where, okay, you can choose these boundary conditions quickly rather than, because that was a big unknown, right? Unless you have some data from experiments, you could not choose the right boundary conditions. Just a thought. Because I used to design turbines at one time, turbines and pumps and all that. So that was like going back to school.
Yes, and I mean, that's very much part of the ease of use, and thank you. It's a good question. So I'm obviously not showing the software today, but for every step, boundary conditions, materials, setting up the analysis to solve, there are wizard selections to help guide the user to make sure they're making the right choices. Selecting the boundary conditions is as simple as picking from a menu, but you're actually applying it to your geometry, your CAD geometry. So, you know, as a user, you'd understand how the product is going to function, how it's tested, or how it's going to work in the real world. So you're applying those real-world conditions to geometry that you understand because you've created the model. So in the software, you have a selection box, and maybe it's as simple as putting a flow rate on. You pick the surface where the fluid enters, click flow rate, enter the units, enter the value, and you're pretty much ready to solve the analysis. So we streamline this as much as possible, but also it's possible to create a template, because if a company is manufacturing the same kind of product again and again, the test procedure is going to be the same. They'll be looking at the same flow rate or same fluids. So a template can be created where a new design can be loaded into that template, and it will automatically apply the correct boundary conditions for the test. So that way, it's a safeguard to make sure the analysis is set up correctly. Yes, sir.
So we are into grain cleaning and sorting business. So in our plants, any kind of so many kind of grains we deal with. So there will be a lot of movement of these grains through conveyors and
Mm-hmm.
bucket elevators and so many machines it has to go with. So when you talk about this CFD, it just only deals with gas and liquids, or some, this grains, the grain particles also, it can be treated as, like same as a liquid. And it's so many of few of our machines, it is a mixture of, air and grains.
Yeah.
Air and granule particles.
Yes.
So that is how we work. So can this CFD can be applied into, we can test our how actually our plant will work before we install our machine into the production line. So, and also we have to deal with lot of dust in our plants.
Yes.
So this dust is a major big challenge for us to deal with. So can this CFD really help us in some way?
Absolutely. Yeah, that's a fantastic question. So we have a lot of customers that are using it for that purpose. So firstly, you mentioned about grain. So in a processing application, the way that would be represented is the fluid is air, but you have grain inside the air. And so when you run an analysis, you can choose to add particles. The particles are often used to simulate erosion, but they can simulate material that's in the airstream. So those particles you can specify to have a given size and density. That gives them a mass in the flow stream. So let's say we have a flow stream moving from right to left, and we have particles that are entered into that flow stream. Those particles will move in that flow stream, but they're going to be heavier than the air. So you'll then see where they're going to move, the trajectory that they're going to take, and they'll fall under gravity as they move out of the flow stream. So we actually have one customer that produces equipment for food sorting, and one of the products is rice, grains of rice. And so the grains of rice come down a shaft, and there are cameras. I know this sounds a bit extreme, but there are cameras that check the quality of the grains of rice. And if there's a grain of rice which is the wrong color or the wrong shape, compressed air is sent to that region, and it fires the grain of rice into a reject chute. So they're actually able to simulate with CFD that exact process. So they can design where the reject chute should be, they can design the pressure for the compressed air to make sure that it sends it on the correct trajectory. So yes, it can solve that problem. But also the question about more of a kind of production line, factory ventilation question, yes. So it's being used a lot for factory simulation, for local HVAC to remove dust, particularly in food processing, or to prevent cross-contamination in a food processing or pharmaceutical industry. So again, dust would be the particles that you'd represent in the simulation. Yeah. Thank you. Yes, sir. To calibrate the...
Yeah, to try to mix the real world with the simulation.
Yeah, I mean that's a good question. Partly to make sure that what you're calculating is representative. So you can calibrate a simulation model to take into account real world test data.
In real time? In real time?
Not in real time. Not in real time. But let's say you've got. For many of our customers, when they first start using the software, a good place for them to start is with a product they have data for, test data. So they would represent that actual physical test to show that it's producing the same or similar results to what they're seeing in reality.
All right, thank you.
Autodesk is bringing generative design in its products. Can we use CFD with it? Is it integrated, or is it in the pipeline to use CFD with generative design?
You know how much I'd love to answer that question. There's a lot of investment at the moment in generative design and simulation in manufacturing, but unfortunately I can't lead to where that's going to go or time frames. But it's something that we're looking at. Yes. Yeah.
So I'm a product designer, so my work majority is with the surface modeling softwares. What I want to know is, can you use, since it's cross-platform, right? CFD, can you use surface modeling softwares, surface modeling files into CFD software? So I know the answer, but
well, you know the answer. So it needs to be a solid model. It needs to be a solid model. It's possible once the model is inside CFD, to create and simulate a surface or a surface analysis. For example, if we're simulating a fan rotating, we don't need to simulate a solid fan. It could be just picking a surface, the front or rear surfaces, giving it a mathematical thickness and simulating it using shell elements. But the model needs to start off as a solid model. Yeah. Any further questions? One more.
Hello. I just want to ask, does this CFD softwares can be used in a leak testing machines? Like we design a leak test machines, so we have a density of the air and the pressure, basically, which is normally given by the customer. But can we basically using this software, can we determine like value of the, what pressure and what density we can use? Because we have a CAD models already in our inventor. So using these CFDs, can we integrate it for the leak testers?
Yeah.
Can you predict where would be the leakage, highest leakage chance?
Yes, yeah. I mean, basically, it's simulating whatever you've prepared in the CAD model. So when you're running a simulation, there's a lot of quantities that are calculated by default, viscosity, density, depending on variables that are used for the analysis. So you'll get a lot of that information. And of course, there's connections with, we have a product called Nastran in CAD, which is now part of our design and manufacturing collection. So the results of the CFD analysis can be automatically opened into Nastran in CAD. So you can run a mechanical analysis there. So in a product, there could be pressures that could be causing the part to deform, where there could be leakage. So you've got a complete solution then. You can predict if that's actually going to happen. So yes, it will calculate the results that you're looking for. Yeah.
Okay, cool.
Okay. So thank you very much, everyone, and appreciate your time. Thank you.
Excuse me. Hello.
Oh, okay.
As he said, he is using grains for filtering the grain structure and removing the materials. Can I find, can I give an input to where the airflow mixture with the moisture content? Can I find the material will absorb the moisture, or the material we are using will affect by the moisture and as well as the pressure flow of the air?
Oh, that's a great question. Kind of yes and no. So you can run a simulation with moist gas, so moisture inside the airspace.
Every place has a different kind of moisture into the air.
Yeah, I understand where you're going. So yes, you can simulate an environment where there's moist air. So in the analysis, you can, based on airflow conditions and temperatures in a space, you can calculate at any location what the relative humidity is. So you can see where there's areas where the fluid could be condensing, for example. But what it won't simulate is the absorption of moisture into a product. That's more of a kind of chemical process.
Not into the product. Maybe it's into the product which is a metal product.
But on
will the surface properties will change or differ? Can we find that?
Yes, so on the surfaces of that product, yes, you'll be able to find out what the moisture levels would be on the surfaces. Yeah.
Because we can able to identify the humidity and moisture in the current place, but we need to find which deals with the product.
Yes. So the results will take you up to the surfaces of the product, but no further. But that probably should give you enough information for what you need.
Okay. Thank you.
Thank you. Okay, thank you very much.
So thank you so much, David. That was really very insightful.